FA Biochemistry. Now we're in part 3 where we're going to talk about the biochemical implications of delta G. So we're going to write expressions for K, also known as KEQ, and also Q given a chemical reaction. We're going to predict changes to K based on perturbations to equilibrium. Compare delta G naught, that's what this little guy is, delta G naught prime. Compare homeostasis with equilibrium because they are not the same thing. And finally, explain how unfavorable reactions are thermodynamically driven forward. So just jumping right in here, here's our chemical equation of what's going on. We have A moles of reactant A, B moles of reactant B. We have a reaction, C moles of reactant C, and D moles of reactant D. So mass action is K, also known as KEQ, because this occurs at equilibrium. You can write it either way, I'll know what the heck you're talking about. This relates the concentrations of the products to the concentrations of the reactants. You don't actually plug in units here, but the values are equivalent to the numerical values of the moles. So you just plug in the number, not the unit, just to make sure that all the units cancel. So concentration of C to the C moles, concentration of D to the D moles, concentration of A to the A moles, concentration of B to the B moles. Okay, and so this occurs at equilibrium. And this really tells us a lot about whether this reaction favors the products or favors the reactants. So if K is large, then the values on the numerator here must be very large, and therefore the products are favored. If K is small, then the denominator must be a large number, in which case the reactants are favored. So it's important to note that K is a constant. This is also known as the equilibrium constant because it occurs at one point in time when this is at equilibrium. When a reaction is not at equilibrium, we have another option called Q, and it's the same thing, except this would not be a constant value. This would be calculated at one moment in time that is not equilibrium, and it can give you an idea of which direction the reaction is heading, if it's heading towards completion or if it's heading towards the reactants. So this is not a constant, and this is also not at equilibrium. So that's really the difference here. Otherwise, the expressions themselves are the same. We just use a different symbol to show that this is a constant, this is not. You'll have to calculate this at each moment in time. Okay, so what if we have a situation where we have this reaction going on, and then out of the blue we suddenly increase the amount of A. So suddenly we have a lot more A. What Le Chatelier's principle says is that the equilibrium will respond to try to reestablish this number. Okay? So if we suddenly have a lot more A, what Le Chatelier says will happen is that the forward reaction will increase to try to reestablish the equilibrium that this reaction would typically have, to reestablish this value. So after we've perturbed it, we could use Q to figure out which direction this would go, and we would see if we add more A, it's going to suddenly favor the products. It's going to shift it in this direction. So keep Le Chatelier's principle in mind. Similarly, if we increase the amount of D, the equilibrium would then shift to the left, and suddenly we'd favor products in order to reestablish equilibrium and this equilibrium constant. Okay, so I hope you guys remember Le Chatelier from general chemistry. Okay, moving on. Now we're going to introduce this concept of the chemical standard state. That's going to be very important for differentiating what's going on with all of these different delta G's. So the chemical standard state has a standard temperature, It has a standard pressure, and it has a standard concentration. So the concentrations are all 1 molar. The pressure is 1 bar, and the temperature is 25 degrees Celsius, which is about room temp. Okay. So we need these chemical standard states because the temperature of a reaction will certainly change the amount of products and the amount of reactants. It will help speed up the reaction in some instances. The same thing with pressure. And additionally, we just define all the concentrations as 1 in order to make the math so much easier for us. So under these conditions, this is all called this chemical standard state. So when we're talking about this in terms of delta G, so remember delta G, we used this to determine if a reaction is spontaneous or not. So you can use this to look at spontaneity. And this is based on actual concentrations. Okay, in the solution, this is what would actually happen. When we have a chemical standard state, we add a naught to the delta G. So this is the delta G at standard state. So at this state, we can no longer predict whether or not these reactions would be spontaneous, if they would favor one direction or another, because instead of using the actual concentration, we are pretending that all the concentrations are 1 molar. Okay? But this is extremely, extremely useful because we can use this knowledge and create all sorts of tables and all sorts of assumptions based on these numbers. And just to really drive home that these two values are in fact different numbers, there's an equation that relates these two together. The derivation can be found in your textbook, but I'm just going to write out the answer here. So that's delta G, so this is the spontaneity of the reaction. We can look at the standard state, free energy, plus the gas constant, the temperature, and the natural log of Q. So that's the ratio of products to reactants considering the moles. Okay, so in this way, we've got this standard state, which is kind of like a reference value. So this is our reference number, and then this is related to the actual concentrations of the products and the reactants. So after we're beyond equilibrium, we can use this reference number and the actual concentrations in order to calculate delta G. So this is very, very important. This equation is very important. Okay, so this particular very important equation is at any point that is not at equilibrium. So if we remember what equilibrium means, I'm going to use a different color here. Equilibrium means that delta G is equal to 0, and also this would have to be the natural log of K, not Q, because K is the equilibrium constant. And if everything else is the same, delta G naught plus RT times this, we can actually get an expression for an equilibrium value that looks like this. Delta G naught equals negative RT natural log of K. And so this is at equilibrium. So this is a way that we can find the standard reference number, the delta G naught, at the 1 molar concentrations of the products and the reactants at the standard temperature, and this is the gas constant. So you can see that this is always going to be a constant number, whereas delta G can change based on the actual concentrations at that moment. So this is always going to be the same number, this number is going to change. Alright, so now's a really, really good time to point out the difference between homeostasis and equilibrium after we've talked about this. Okay, so homeostasis is like a set of conditions under which life processes can occur. So this is like the standard state. So this is the conditions of life. So this is typically pH 7, body temperature, whatever. And we use energy in order to maintain homeostasis. Equilibrium is a specific point, and it is entirely based off of delta G. On delta G. Definitely never based on delta G naught. So these two things are not the same thing. So homeostasis is or homeostatic conditions are the conditions of life. Equilibrium is when delta G equals 0. And these two are very, very different, just like delta G and delta G naught are very, very different. Okay. And then the final delta G that we're going to talk about is delta G naught prime. So this is the biochemical standard state. Okay. So consider the following. Why wouldn't standard state be good enough for the biochemists? Well, that has everything to do with pH. So, what is the pH when the concentration of protons equals 1 molar, as in standard state? It is not pH 7. So in biochemical standard state, what we need is a concentration of protons of 10 to the negative 7th molar. So this would give us pH equals 7. This is the condition that we are really, really looking at. So the temperature is the same. The pressure is the same. It's just that this concentration of protons has to be this value, not that value, in order to get pH 7. Also, the concentration of water, which typically is 55, is assumed to be 1 molar, so it just falls out of any equation. So this is the difference between the biochemical standard state and the standard state. Okay. Other than that, delta G naught prime is again a constant, just like delta G naught was a constant. It's just that this takes into account the pH of life, which is pH 7. So we can have the same type of equation relating delta G to delta G naught prime plus RT natural log of Q. Okay, so in this we just substitute delta G naught prime for delta G. Delta G naught, rather. So now we're going to address how unfavorable reactions are thermodynamically driven forward, and you're going to see that this is based on delta G. Okay, so we looked at this equation a little bit ago, and we saw that delta G equals delta G naught plus RT natural log of Q. We also made an expression for delta G naught at equilibrium. So if we plug that expression in here, we get this expression. So we just substituted this for this. We have delta G minus RT natural log of K plus RT natural log of Q. So now we can pull out the common RT from both sides and end up with this expression. RT times natural log of Q minus the natural log of K. So there's the negative sign. And when we simplify this further, we get delta G equals RT times the natural log of Q over K. So this equation really describes that delta G is the driving force for these reactions, but so is Q and so is K. So because this is a constant, this is a constant. So these three things determine whether or not a reaction is going to proceed forward. Okay, so whenever this ratio of Q to K is less than 1, the reaction is going to proceed as written. Okay, so therefore, we can drive a reaction forward if Q is less than K. We can also drive a reaction forward by coupling an unfavorable to a favorable reaction. Favorable to unfavorable. Because, if you remember, delta G is a state function. So that means it doesn't matter the path that you get from reactants to products. What matters is the actual values. So we can change the delta G for a reaction by adding in a step that's really favorable. Okay, and we'll do some more problem solving with that in class.